screen, if that's okay with you.
Yes.
Has it happened? Yeah.
Yes.
Yes.
Full screen.
Okay.
Yeah.
Yeah.
Thank you.
So I hope that has come on. Yes. All right. First, some clarification. This is not an experimental talk. I'm a theoretician. I'm trying hard for some experimentalists to pick it up and actually achieve it in experiments. Apart from that, thank you very much for giving me this opportunity. I would particularly like to thank Professor Panigrahi for spearheading this fantastic set of lectures for last 3 years. I think now it's 2023. So QIQT23, I'm really honored to have participated in all of them in some manner, and hopefully there is something interesting for me to share this point in time. All right, so I'm going to talk about quantum tunneling, the very, rather the poster boy of quantum mechanics. And interestingly, amazing amount of experiments have been done. Though at the outset, let me clarify that there is no interferometric measurement of the tunneling time, which seems like a reasonable thing to do yet. And hopefully the proposal which I shared with you, I'm expecting some experimentalists who are extremely talented to anyway pick it up from, from the papers and pens of the theoreticians. So, all right. So the system we are talking about is a very realistic system. Just a broad outline. I'm not going to touch upon most of this part. So which is, I'm going to look at photonic crystals, defect states. I can say these are all our tools on which we build the interferometer. Then there is a cavity, there are orthogonal states, there is perturbation. The way we think about it is symmetry breaking. We create superpositions, we have waveguides, all kinds of stuff. Then we have the propagating fields and evanescent fields, and eventually we have the interferometer. So it's a longish journey, but I will not bore you with all of it. Let me just get to the point. Okay, Dr. Sen, may I know how much time I have? 20, half an hour, is it?
No, it's 45 minutes.
45 minutes, fantastic.
Yeah.
So I have all the time in the world. Thank you so much. You have been very kind. All right. So tunneling time. So I'm just getting back to very, very basics. The quantum mechanics permits a particle with an energy that is lower than a barrier, which it encompasses in the front. If the energy is lower than the barrier, then the particle can tunnel through, and that is very quantum mechanical. It's not some esoteric phenomena. There are lots of devices which actually are built on that principle. Of course, classically, if the energy of the particle was lower than the barrier, it will simply get reflected back. Now, what happens is that in quantum mechanics, of course, the particle does tunnel. There is a finite probability which you can calculate, and it's calculated probably in the first year, master's course in quantum mechanics, undergraduate maybe. And one can calculate the probability. One can, it's very deterministic. Everything fits in very well. The formulas, all the associated computation as well as analytical, expressions are all there. There's nothing surprising there. But the question one can ask is, what is the time that the particle required to complete the tunneling process, right? Now, that is a part which is a little dicey, and there has been no convincing answer to that. It so happens that, there is wave-particle duality, which quantum mechanics anyway throws up. We have just heard the previous talk, which had some touched upon amazing philosophical questions about it. But you see this spread, so what happens, you spend in a particle, but the quantum nature makes it like a spread thing. So you really can't pinpoint the precise time it sort of entered and precise time that it got out. And then one can interpret as to what exactly we constitute as a particle having tunneled. So there have been various types of times that people have invoked, various definitions. Variety of these have been measured. But something interesting is what I want to point out. So the point is the following. It so happens that people figured it out very, very long ago. Hartmann, very early on. It's called the Hartmann effect, which is that as you keep increasing the size of the barrier, the time it takes for the particle to go across saturates. What that means is, even if I keep increasing my barrier size, the particle tunnels faster and faster, so as to maintain that the time is saturated. And that would mean that particle in principle can travel at superluminal speeds. Okay, so let me not get into the interpretation of whether this constitutes a signal. It does not. But the fact that a particle can tunnel, and these have been measured experimentally, seems to be that if I take the same region and let the particle propagate in free space, the particle sort of arrives slightly earlier than it would under the tunnel than it would otherwise, right? So there is an issue. There has been measurements. There have been multiple measurements, and it's a very active area of research. Very recent 2021, 22, maybe Nature paper, I'm mistaking the year, but they have done it with BCs and, wherein the particles themselves hold a clock and so on. I'll just talk about it briefly. But, there's a lot of discussion. There's a lot of issue. And what we want to, in this talk, I want to limit myself is that, is there a better way to measure that tunneling time? Right? So there are these various times which I list out here called the dwell time, the transmission time, the traversal time, the Wigner time, the Buttiker time. There are all these definitions, all interesting, all need to be studied. And one has to see, where do experiments match up, right? So that's a question which probably remain unanswered because the experiment is not done. What I can show you only is simulations, and we hope that the experimentalists will do the needful for the rest of it. All right, so let me just talk to you about the main issue, which is the Hartmann effect. I'm just repeating myself here. So, for example, in thin barriers, as you increase the barrier thickness, the transmission time does increase. But as you get to thicker barriers, right, it so happens that the transmission time is independent of the barrier thickness, right? So, for example, how is this measured? This is a typical experiment, just a qualitative picture of what people do. So what people do is the following. I don't know whether you can see my, let me just get hold of the presentation marker. Can you see my mouse, by the way?
Yes.
You can, right? Yeah. So I should be able to get a, sorry, I am now forgetting where do I, all right, I think let me just continue. Right. So what you have is there is this fiber bag grating. What it means is basically, there is a one-dimensional periodic structure in, it's a photonic material, but there is a photonic band gap. That is, you have made sure that you're operating at wavelengths which are not permitted across this barrier. All right. So what will happen is, if I put in light at that wavelength, rather the pulse which is centered at that wavelength and whose bandwidth is limited within the bandwidth of the fiber bag grating, what will happen is that the pulse would largely be reflected back. And you will see that evanescent, the tunnel pulse is the transmitted part, which is exponentially decayed out across the tunnel, and it arrives on the other end, right? So you send in the pulse, and then you look at this fiber bag grating, you look at what is transmitted, but that is just one signal, right? So how do you compare this time that you have recorded versus the time which light would have taken otherwise? So you have to basically figure out the tunneling time in comparison to a free propagation time, right? So what you do is you remove this fiber bag grating and you replace it with a normal channel and again measure the pulse. Then you have two pulses. One is the one without the grating, that is without the barrier. The other one is with the barrier, and you compare the two and then make a statement. Now, this is a very reasonable approach, but there is a problem. The problem is that the tunnel pulse under the barrier had actually dramatically deformed from the original pulse. The original pulse would have been exponentially decayed. And it is a very highly deformed pulse that comes out at the other end. Now one is asking, One is trying to compare that deformed pulse with the unchanged pulse in free space and asking which one traveled faster. Right? So let me just give you an example. Imagine, there is a bus and you are looking at a bus which is full of children, school bus, let us say, and the bus goes through the tunnel. We are interested in the average velocity with which the children traveled under the tunnel. And imagine all the children during the tunneling time under the tunnel, they actually move to the forward of the bus, right, near the driver. You will see that the average number of children have traveled faster than the bus, right? So you see, when you deform objects, it is very difficult to now make a statement who traveled faster, right? So one has to do that very, very carefully. And that is where, there are issues related to interpretation and so on and so forth. Right. So I hope I have conveyed the problem. And people have done something more exciting. This is the 2020 paper. Sorry, I misquoted that. This is 3 years back. So what you have is the following. Imagine I had a system in which the particle which is tunneling itself carried a clock on its head. It will switch on the clock when it entered the tunnel, and the clock would switch off at the end of the tunnel, which seems like the best thing that can happen, because then you just count what has happened in the clock, and you know precisely the time it has taken to traverse. So people have done this, but there is a problem. So let me just very briefly tell you what this experiment is all about. So basically, what you have is a barrier region in which there is a finite magnetic field, right? So the magnetic field is strictly limited within the barrier region. So imagine this was a spin half particle, which was appropriately prepared. So imagine that it's prepared in this state, the xy, in the x plus y kind of square root 2. That's a kind of, it's prepared as a linear superposition in the xy basis, and you're applying a magnetic field along the z. What would happen is that this spin will actually precess about the magnetic field, right? And how much it precesses, that is, as it comes out, if I can measure where it is, then I know from my initial preparation, I know how much time it has spent under the barrier, right? Now, the problem with this experiment is indeed fantastic proposition, actually done very early by Whittaker and Landauer. They had suggested this, done a lot of work very early on in probably 1950s and so on, 60s maybe. And then, what happens is the spin not only precesses, it also tries to align itself along the B field. Right. So now you have a problem. It is not merely doing something, it is doing a little bit more. So what they came up with is that they measure two types of time scales. And it is almost like invoking some sort of one would call equivalent to an imaginary time. A real time is the precision about the Z, whereas there is an extra time that is to align itself along Z. So there is again a problem of how do you go about interpreting these results. So what I'm saying is there are these just two family of results, and you can clearly see that there are going to be multiple problems in each proposition that one puts in. Each experiment has its own limitations, and so let's see whether we can do something better. All right. So the model that we are proposing, this is work done with my student Gagandeep Kaur, who has just graduated. So what we propose is the following. Imagine I had an interferometer, because interferometers offer us the best state-of-the-art precision in measurement, whether it is be time. It can be done both in the temporal domain or in the spectral domain. That is, you measure the phase or you measure the time, and you can do both of this with extremely great accuracy. Now, the problem in many of these earlier proposals was the following, that you are measuring basically apples and oranges. One was an undistorted pulse and one is a distorted pulse. So what we thought would be a fair measurement would be, imagine a Mach-Zehnder sort of a interferometer. So please focus, sorry for this very cluttered slide. You have an input pulse, which is normal. And then what happens is that the pulse gets split into two parts at the beam splitter. And then it tunnels through one barrier. Exactly similarly, it happens in the other barrier. Again, it propagates maybe. Then it tunnels again, right, in these two. And there is a slight difference, controllable difference between the two tunneling paths that the particle can experience across the tunnel, and then you measure the outputs, right? If you can construct such an interferometer, then you see you'll be actually comparing pulses which are only slightly different from each other, and probably will give you interferometric accuracy in terms of measurement of either the phase or the time in such an interferometer, right? And so that is precisely what the game is. So we can come up, we can do this very simple one-dimensional analytical calculation across these two. We have done that. The expressions shown are below. Basically, you can come in with a particle which has got an energy slightly below the barrier height or just above the barrier height. And again, we want to compare. So we call the first one as the first one as the evanescent field, or the tunneling sort of a situation where where the energy is below the barrier height, and this situation is where the energy is above the barrier height, right? Which is the propagating, the usual kind of interferometer, where you accumulate a phase or optical distance or optical phase depending on the energy difference between the barrier and the particle, right? So that's why the words EFI and PFI, which means evanescent field interferometer and a propagating field interferometer. All right. So you see, this is what we are having, just to make sure that we are on the same page. We have a particle that comes in. Okay, I'm looking at it as in the basis of plane waves, for example. You have IKX coming in, you have a reflected part, and you have a transmitted part. And again, you have, some transmission coefficient times the original. And, in this region under the barrier, you have basically exponential plus kx and minus kx. These are the only things that are there. And one can do all the little analytical work and get to all the transmission, the phase accumulated by the particle across, and from there one can sort of interpret as to what the time is, right? So I'm just giving you something to tell you that this can be done very systematically. Let me not waste time. Depending on your energies, either you get cos and sine hyperbolics, or you get cosine and sine functions, harmonic functions. One can do this. And so if you just calculate this and you ask now at the output what is happening. So let me just tell you what is happening for the evanescent field. It so happens that as you keep increasing the size of the barrier in one of the arms with respect to the other, remember both arms have got barriers. You are coming at an energy which is lower than the barrier height. So you are in something called the evanescent field interferometer. And then these are just analytical calculations. So I'm just showing you what it turns out to be. So once you're tunneling on both sides, you are now increasing in one of the arms the barrier length a little bit, or a height, depending on, I'll tell you there's a nuance to that. But as you increase that, you see that the output intensity sort of, this is the way you would get on the top, where if you correspondingly determine the phase, you will see that the phase actually saturates to pi/2. Okay, as you go further and further, you see that the signal keeps decreasing. That is because as you increase the barrier height, smaller and smaller amount of the field is coming out. In that sense, you are losing the transmission itself is becoming very small. So of course that will depend on the accuracy of your measurement, and hence the overall visibility, of this interferometric measure comes down. But you see that in the limit of a large barrier height, that's where Hartmann would come in. The phase actually saturates to pi/2. Okay. Whereas in a normal interferometer, you do know that if I come in with a energy of the particle which is above the barrier height, or it's a freely propagating particle, I can keep putting in some different phases, right? Or put in extra refractive index, for example, in the arms of a Michelson interferometer. And as I keep increasing the size of my phase element, I will keep increasing my phase from 0 to pi to 2 pi to 3 pi. So basically the phase will keep on accumulating, and I will see this oscillatory behavior in the intensity of light, right? So you see that there is clearly a dramatic difference in the phase accumulated by the particle under tunneling conditions. You see that you do not actually keep on increasing the phase as you would increase in a propagating sense. What you get is a saturation at a phase difference of pi by 2 between the two arms as you increase the size of the barrier. All right. Now there is the other, as I said, I'll get back to, so for example, let me just go back to my original model. So imagine that you increase the size of one of the tunnels. I'm not increasing the height, but increasing the length of it, for example. Now you see that if you increase the length, the free space propagation will again, because of the increase in the length, the free space propagation in both the arms will be unequal, right? Then I'm not compensating properly. So what I do is whatever I increase, rather in both the arms, I need to make sure that my free space propagation lengths are exactly equal. That is, if I increase the length of one of the barriers, in correspondingly, I have to decrease the free space propagation length in the other arm, right? Otherwise, I would actually start seeing. So that is why I'm saying this number one is when you have the evanescent interferometer, where I increase the size of one of the barriers, but did not bother to compensate for this free space propagation phase. In that case, you still continue to get, this phases beyond 2 pi, beyond pi by 2. So this is a pi phase, and then as you keep increasing, you'll start getting more and more phase. Only in the part B, which is what I showed you earlier, where you have made sure that if you just change, for example, the height of the barrier, then the free space propagation is equal, or you increase the length of the barrier but compensate the loss of free space or equalize the free space in both the arms propagation, and then you get this saturation to pi by 2. And of course, the C situation is when you have the propagating field. So you clearly see this is a phase difference plot where you see this this purple line is for the saturation that would happen at pi by 2, whereas for the other case, either uncompensated or the normal interferometer, the phase will keep on increasing as you increase the path length. All right. So let me just tell you what we have done. This is all theory, fine. It works out analytically. Let's see whether one can implement it. And so what we did is the following. So please concentrate your attention on the right side at the moment. So there what I have is basically I have an input here. This is a photonic crystal, right? And I have created sort of defects in this photonic crystal. The defects are 4. There is a larger rod here. There is a larger rod here, here, and so on, right? So you see these 4 rods. These are basically defects now. So these turn into optical cavities actually. And these cavities can have very large Q factors. That is, if I put in light within this cavity, within the band gap, of course, with the frequency of the pulse or the light field within the band gap, then the light field remains confined within this cavity. But because these cavities, apart from the field that is there within the cavity, the fields actually evanescently decay around the central cavity. You see that the field actually leaks out along various directions. And that leaking, the evanescent part of the field is actually exactly same as tunneling, right? So what happens is that the field equivalently tunnels towards the top here and towards the right. Again, the field is sort of put back and made to tunnel in the vertical direction. So this is the Mach-Zehnder arms, and then they combine together, and this is like the new beam splitter that throws out the field in the propagating modes along the detector D1 and D2. I hope the the setup is clear. So these two red boxes act like beam splitters, and the region between the boxes is actually the tunnel, the barrier. And one can basically, to change the characteristics of the barrier, we can change the size of these intermediate rods, either in this horizontal. Imagine I increase the size of this rod. That would mean that I increase the optical density for the evanescent field. That would mean that equivalently I change the barrier height, right? And then I am looking at how does that change, which I have incorporated in this, actually lead to the changes in my detector D1 and D2, and one can measure the appropriate phase. So this is the playground on which we are dealing with. There is a small nuance which I should tell you. You see these little dots, these are not mistakes, but these are basically small perturbations given rise, are being put in to basically mold the evanescent fields along specific directions. All right. So this is something that we have done, and I will give you the reference later. We have done a detailed analysis of what these perturbation rods do. They actually create beautiful controllable superpositions of the field inside the cavity, and one can actually use them to make. We have used them to make variety of filters. Wideband, stop band, all kinds of filters, mirrors. You name the device, one can actually utilize these sharp bends and so on within photonic crystals to actually manipulate the field as well as the evanescent fields accompanying that localized field within the cavity. All right. On the same hand, we use the same structure, but we basically open out, remove the rods here. So this is just a propagating channel for the field to bend. And this is your conventional Mach-Zehnder interferometer realized inside a photonic band gap material. And again, we do the same thing. On the left is basically the field profiles. So you see that the input field comes in. I will show you a movie which probably will make it very clear. So input field comes in and the fields basically decay in both the arms, and then they are combined together to give you what you have here, right? And then they are combined and in D1 and D2, and one can. So let me just show you the sort of, it's again, just a small note. Again, there are nuances to this. If you look at the last beam splitter, you will see that there are two dots here. This is to make sure that, after all, we need to have conjugate outputs for this to behave like a interferometer. One needs to have conjugate output on D1 and D2, right? That is, if this is a maxima, interferometrically maxima, the other one should be a minima. And that requires us to appropriately load the final beam splitter. And this is just telling you that, increase in the optical depth in one arm leads to increase in one detector with respect to the other, and the vice versa when you do that. So it is basically ensuring that our defect centered cavities actually behave like proper beam splitters, right? After all, that is at the heart of combining the beams inside an interferometer. All right. So these are the some short results so I'll come back to the details of the issues related to the interferometer, the whole making of the photonic bandgap structure. But let me just first show you the results so that we are sticking to the point. I was under the impression that I have a 25-30 minute talk, so I put the Hartmann effect and evanescent field on the top, but I do have other details which I will share with you. All right. So in the propagating interferometer, wherein you remove those rods, you can clearly see on your left that you see you start getting these fields, which are, they are the phase actually, it gives you oscillatory behavior, which arises largely from the phase going beyond, so at this point it'll be pi by 2, at this point it'll be pi, and so on and so forth. It'll keep on oscillating as you keep increasing the optical path among one of the arms in the propagating one. Similarly, in the evanescent field, one can increase the optical depth of the intermediate rods, which is like increasing the height of the tunnel. And you see that what one obtains is a saturation of this effect, right? And now there could be other sort of, what I call other applications of such an interferometer. Remember that interferometers have a sensitivity largely which is contained within. So if you look at the left plot, which is a conventional interferometer, the sensitivity is largely in the domains where you have put in the arms, and they are more or less equally sensitive everywhere. But if you look at the evanescent field interferometer, that is a tunneling one, you see that the sensitivity is delocalized. You can actually put in a perturbation in locations which are not within the so-called evanescent arms, and yet affect, the way the evanescent fields have tunneled. So, evanescent fields are not usually associated with the phase, because they are just thought of as support systems. But you can actually tailor the phase of the evanescent field, and one can actually also interferometrically measure it. So, and this interferometer probably gives you that idea. So anyway, so the intermediate conclusion which I want to offer is that we have realized the evanescent field interferometer, and one can actually do this both in the spectral as well as the temporal domain. I have not shown you the temporal movie yet. I will get opportunity by the end of the talk to show you that. We believe that is the first interferometric measurement protocol for the Hartmann effect. There is a high sensitivity for the interferometer arising out of the spatially delocalized fields which are there here. And we are hoping that when done appropriately with appropriately compensated paths for the free space propagation, one can actually detect and measure pulse reshaping, including the superluminal pulses, and characterizing them well should be possible with interferometric accuracy using such an interferometer. And of course, the open question remains the true quantum nature of, for example, entanglement. Maybe you put in an entangled pair in one arm, in these arms, and look at how that quantum, the over and above the tunneling, the quantum feature, how does that sustain within these barriers continues to be an open question. A lot of this work is actually can be found in this 4th publication, which is just come out this year. But the lot of the control of the spatial modes is what I want to dwell on, maybe just about 10 minutes, so that you don't think that it has just come out of the blue. Let me just tell you what exactly we have done in terms of very fundamental and very sort of a very overview of what we did. So you see that once I create a photonic crystal and there is a defect, there is a governing symmetry, right? So for example, in the square symmetry, we have precisely these, C4 rotation, and there are 4 vertical planes, so we call it C4V symmetry. And you see that basically if I rotate the fields appropriately, you will get at 90-degree rotation, you will get back the same thing, including there are vertical planes across which can be reflected. Yeah. All right. So we are looking at such a system, right? So there is a governing symmetry. That would mean that it commutes with a few things. That would mean certain field profiles remain unchanged, and where we basically solve a eigenvalue problem, which almost looks akin to the quantum mechanical eigenvalue problem, and one can actually map it. All right. So what we do over and above this is that once you have the system, I have highlighted here this little dot, which is a small, I would say, a perturbation to the defect. The defect is the central one that is giving rise to a defect in the overall setup, and there is a perturbation to that defect. This perturbation to a defect leads to basically, bound. So this perturbation, the larger dot here at the center, leads to two degenerate states within the band gap. This yellow region is the band gap. So if I had, if I had a perfectly aligned crystal, without this defect, I would just have a pure band gap. Moment I put in a defect, I see I get a band gap. And within the band gap is already there. Within the band gap, I get states which are actually able to transmit light, right? So these are defect states within the band gap. Now, once you put in this extra perturbation, the degeneracy between the two states is lifted, and you actually see that these become non-degenerate. So let me just tell you what is happening. So if I just come in with the, so please keep your attention on the right top. Without any perturbation, I get a field, a dipole field. These are the two modes. The dipole field, which is aligned along the horizontal direction, and the dipole field aligned along the vertical direction, right? Now, as I introduce the defect, here. You see that the field is aligned along the defect and orthogonal to the defect, right? So you see that I'm able to modulate the field which is within that domain by introducing this defect and systematically varying the characteristics of that defect. So not only at 45 degrees, at any other angle, one can actually have this defect. And we actually clearly figured out and also computed it, as well as analytically derived the superpositions that we are creating. So X and Y are the corresponding superpositions of the dipole modes aligned along X and aligned along Y. By introducing a defect, one is creating a superposition which leads to the overall alignment of the orientation of the field in the direction theta. And there are two modes. One is parallel to the location where the defect has been put in, and one is perpendicular to that location. And there are other phases that come in, which again we have characterized. So the way we are thinking about this is the following. This has been done already. That is, you have a periodic structure, you have a defect here. So this acts like a cavity. But imagine this material would exhibit, for example, a Kerr nonlinearity. That is, in presence of a light beam, it would change the refractive index. So imagine I could do something like that dynamically. I would create a very localized perturbation to this cavity, right? And that perturbation, which could be dynamically controlled because this is applied externally, could actually be used to create what I am talking about in the photonic crystal. Now, this kind of, basing all these arguments on a defect is very ubiquitous. It is actually, I don't know why it is not taught in our typical courses. It is just a 2D potential. And, if I put in a defect, you see that the wave function gets pinned down to the defect. As I move it around, I can basically manipulate the wave function. And now the modified wave function can be written as a linear superposition of the original set. And one can actually do this very systematically. So once you have this, the cavity, one can actually put in waveguides, which are connecting to that cavity, because you can launch in light here. The light can be, it's like a turnstile where you can make the light go in whichever port you would want. You could have multiple input and multiple output ports. And we have shown all of this. These superpositions have been worked out with great detail. And there is a lot of control actually. Then one can get, as I said, narrow band filters, wide band filters, where you put in light at the range of frequencies that you want. And depending on the perturbation, one can basically make it go in the direction that you want. And for example, I can come in with two sources, and this is my region where I can play around with, and figure out what my transmissions are. This is a completely quantum mechanical calculation. And, these dots and circles, rather these circles and triangles are through our analytical formulation. And these lines are coming from the computation. So you see that the analytical creation of the superposition with the appropriate phases has been realized to a great degree. One can even, for example, get a sharp bend, without doing too much by just introducing this small little perturbation and so on. One can get a beam splitter. And this is what I had used for the interferometer, where one can get a beam splitter and actually in a controllable manner, it's a sort of a tunable beam splitter where you can put the light in the forward direction or in the vertical direction. You can play around with whatever you like. And basically what has happened is that one can provide mode rotation, maintain orthogonality. What is amazing was we did not create the orthogonal field. One mode, sort of aligned itself along the perturbation, whereas the other mode became spontaneously orthogonal to it. That's the way nature works. So that orthogonality is maintained. It's a perturbative effect. One can basically play around with the modal distribution, and one sees that if there are null planes in the modes, then in those directions there is very little waveguide coupling. One can sort of change the mode profile by increasing the perturbation and so on. So there are some parameters. This is actually viable even in, for example, in a hexagonal lattice. One can do this, and we have done in a hexagonal sort of a 6-port beam splitter can be done, where you can put in the field in the direction that you want. So I will probably not bother you too much with this, and with this I will probably stop, and I will simply share with you the references where probably you can, if you're interested, you can look at the more details of this work. Yeah, thank you very much. I'll be happy to take in questions if there are any.
Thank you for finishing well in time. So
Yeah.
the floor is open for questions. You may raise your hand or unmute and go ahead.
Do you want me to stop sharing, or?
No, it's okay.
Okay, fine.
Yeah. Sorry, Sangeeta, I have a question.
Yeah.
Yes, please.
Yeah.
Yeah.
See,
Yeah,
I
hi,
mean,
Harsha.
it's really fascinating that, this kind of thing was not earlier done. I mean, this kind of interferometry is really fascinating. I mean, you are essentially now, traversing bound state and, this traveling states, that kind of boundary.
Yes,
right?
yes. And I mean, it's a very simple calculation. It is not tough.
But, and also since, you are talking about the speed, is it possible to use it like a memory? I mean, can you sort of in a control way?
Actually, no. So let me just tell you what my thought process was. What I thought was, once you create a cavity, one can make the wave packet bounce back and forth, and hence control the tunneling time, right? In a sense, you are writing off the phase into the evanescent field. And actually, if you look at, they have got quality factors like 10,000 and even beyond, maybe about 1 million now with photonic crystals. So I don't see why there is not a possibility of making it into a controllable memory device, right? I mean, certainly possible. And what we think would be, sort of our small contribution is that using perturbation, one can dynamically control that characteristics. And we have sort of used it to control the evanescent field and the tunneling direction. So we do believe it is very powerful.
Yeah.
And I'm just hoping that some experimentalist does it so that, at the end of the day, a theoretician feels fulfilled.
Yeah.
So that,
very fascinating. Very fascinating. Yeah.
Thank you so much. Yeah. All right.
Anyone else? Okay, Ranjit Singh has raised a hand.
Yeah,
You can
please go ahead. Yeah.
Thank you for your talk. I have one clarification question. So, you showed analytically a way of considering interference or overlap of two wave functions, for example, while propagating in a waveguide, not waveguide, closely placed waveguides. So,
yes.
Yeah. So my question is, do you suggest or you use numerical software packages which are relevant for modeling complex interferometers?
Oh, yeah. I mean, so for doing many of this is analytical calculation. That apart, for looking at pulses through this, we are little suspect about commercial softwares. So I do not rely, but you can use COMSOL and numerical and all that. But what we have done is we have gone back to the MEEP software, which is open source, available and developed by the MIT group. And we have basically used that software to create our systems. And so anyway, we did check and confirm that these simulations that we have done also hold good in console. So there are multiple avenues where one can actually create these interferometers, any for that matter, any optical structure, and one can simulate that. So there is a finite difference time domain technique, and there are other frequency domain techniques through which this can be done. Yes, certainly.
Okay, thank you.
Yep. All right. Yeah.
Okay, so if there are no further questions, I thank the speaker once again for a very, very interesting bridging talk in some way.
Yeah.
So,
Thank you so much.
Thank you so much.
Thanks a lot. Thanks a lot. Yeah. Bye. Bye.
Bye. So we close the conference for today. This is the last talk for today. So hope to see you again in the next talk.
Sure.
So bye-bye.
Bye. Bye.
Thank you. Bye.
Thank you.
So thank you for participating, everyone. So we end the session now.